Hello, I am Max Apodaca and I will be explaining how to write equations for curves and surfaces in 3 dimensions. To start off, I will explain why a y equals mx plus b-esque equation does not work. When you try and write an equation in 3 dimensions using a y equals mx plus b equation as a base, you might get something like y equals z plus x. But if we graph this, it does not create a line because there are multiple values that z and x can be for any given y. Instead, this creates an infinite number of lines in 3 dimensions next to each other, creating a plane. So how do you create a line in 3 dimensions? To answer this question, I will first explain how to write a line in 1 dimension. Let's start by figuring out what a line really needs. A line needs a starting point, for which I will use D, and a direction, for which I will use A. We can then create the equation x equals at plus d. Now, if we graph this, we get a line that starts at D and moves forward by A every time t increments. You might be asking yourself what t is. T is what mathematicians call a parameter. This is used to create a line by plotting all the x's generated from all the t's in the equation. Now let's see how this relates to 2 dimensions and y equals mx plus b. So let's see how we can rewrite y equals mx plus b to make it similar to our 1-dimensional line. Let's start by looking at what slope really means. Slope is the ratio of rise over run, so we can rewrite it as delta y over delta x, just as we can with any ratio. We can also find a starting point in our line, which we also needed in the previous equation, so it will come in handy again later on in this equation. I will label the starting point DE. Now with the starting point and direction, which I've written in vector form, we can write our equations for a parametric line in 2 dimensions. We do this by writing 2 equations, one for x and one for y, each one using its own direction and starting point. The idea behind this is that if we increment t by 1, then y and x will change in the same proportion as they will in slope-intercept form. We see this in the diagram to the right. The line starts at DE, then moves back by a in the x-axis, and by b in the y-axis if you decrement t, and forward if you increment t. Let's try it with a function. We'll parameterize y equals 1.5x plus 5. Our slope will be 2/3, which will yield an a of 2 and a b of 3. We don't have a starting point explicitly given, so we will use the y-intercept because it's the easiest point to find on the line, but any point will work. So now, with our direction 2, 3, and our starting point 0, 5, we can write our 2 equations, x equals 2t and y equals 3t plus 5. Now, we can graph these to see that it looks exactly like the line y equals 1.5x plus 5. Now let's generalize this into 3 dimensions. The same concepts applied to create the line in 2 dimensions can be applied to create the line in 3 dimensions. You need a direction, ABC, and a starting point, DEF. You then create your scaled equations similar to the 2-dimensional example. These can also be written in vector form as I have shown. This makes no difference to the meaning of the equation, it's just a different notation. If we draw 3 number lines in 3 dimensions and then plot our values on the number lines, we see that for every t we move a in x, b in y, and c in the z-axis, starting at the point DEF. If we now plug in real values into our equations, we can create our first equation for a line in 3 dimensions. The line passes through the points -3, 2, and 4, moving 2 units in the x-axis and 3 units in the y-axis for every 5 units in the z-axis. We can't express the slope of this line as a proportion, because it would require 3 numbers being related to each other, which a proportion cannot do. So, we can now write our equations for lines in 3 dimensions. But lines are boring. We want to be able to write equations for curves in 3 dimensions. To do this, we will replace the functions for x, y, and z, which have only been linear functions until now, with arbitrary functions, f, g, and h of t. If we set these to linear functions, we will again generate the equation for a line in 3 dimensions. There is another notation for these parametric functions, where the functions themselves are written in the ordered pairs. It's just a different notation again, like the vector form for a line, and makes no difference to the actual meaning of the equation. But what happens when we replace the functions with nonlinear functions? For example, if we use cosine of t for f of t, sine of t for g of t, and t over 5 for h of t. Now, if I tell you that the parametric equation x equals cosine of t and y equals sine of t gives a circle in 2 dimensions, What do you think the equation that we have written will yield in 3 dimensions? Pause the video and think about it. Well, we are incrementing z by 1/5 every t, so we are moving the circle up as we draw it. This creates a helix centered around the z-axis, as you can see on the right. Any curve can be represented like this in 3-dimensional space. In the past, all of the 2-dimensional equations you have written have had no volume, so the outside of the object had to be a curve. In 3 dimensions, however, there is volume, and we can create a surface that encompasses that volume, and we can write the equation for that surface. There are 2 types of surfaces in 3-dimensional space: parametric and implicit surfaces. First, let's talk about parametric surfaces. To create a parametric surface, a parametric equation based on only one variable will no longer be sufficient. We have to add another variable. I will use u and v to yield x equals f of u and v, y equals g of u and v, and z equals h of u and v. For the next example, I will use u for f, v for g, and u plus v for h. If we graph this, we get a plane. But you might be asking yourself what the extra variable is for. The plane to the right illustrates the process of layering on top of each other a whole bunch of lines in 3 dimensions to create the plane. This is what the u and v do. For every u, this creates a new equation for v, and then the equation for v is plotted as the parametric equations for the curves and lines in 3 dimensions were earlier. Then the next u is taken, and this is done for all the u's. This puts all the lines next to each other, creating a plane in 3 dimensions. This process is not restricted to lines only. Here are some more examples to illustrate how it would work with other parametric equations in 2 dimensions that have been rotated in some way. On the left, there is a hyperboloid, which is formed by rotating a hyperbola around its axis. The parametric equation for the hyperboloid is composed of 2 parts: the parametric equation for a circle and the parametric equation for hyperbola. The circle uses the parameter u, while the hyperbola uses the parameter v. This allows the circle to scale the hyperbola's x and y values, rotating it about the z-axis. A similar concept is used to create the bonbon surface, which is seen to the right. A circle is used to rotate the cosine function about the x-axis by scaling the y and z values of the cosine function. An implicit equation is an equation where not all the variables are solved for, or in layman's terms, one equation for x, y, and z. Implicit equations can be thought of to work in a similar fashion as parametric equations with 2 parameters. You can think that for every z, it draws a 2-dimensional graph at that z-plane. In the case of the left function, it draws an ellipse for every z value until the ellipse turns into a point. This creates the shape because the ellipse keeps on shrinking in its radius. The function on the right draws a hyperbola for every z value, creating a surface that represents every hyperbola for any given ratio of a to b. This is a helpful visualization tool for 2-dimensional functions because it allows you to visualize every single hyperbola, for instance, of a given ratio of a to b at the same time, without having to plot a whole bunch of graphs to give you a feel for how the hyperbola will change. Thank you for watching my video, and I hope it helped you.